Welcome to Exercise 1 of the iMachining Professor Jumpstart series, iMachining Walkthrough. This example is a step-by-step guide on the definition process of SolidCAM's iMachining technology to machine the part shown here. In this video, we will define the CAM part as well as the machine and work material parameters. We will then perform the rough and finish machining of the outside contour, center pocket, and pocket ledge. As we continue through our video, I will explain the geometry definition process in iMachining, as well as some important points to keep in mind while using the technology wizard. First, we'll need to open our example SolidWorks part. Please note that the example file called iMachiningWalkthrough.sldprt will be included with this interactive Jumpstart PDF and can be opened by simply clicking on the part name inside the PDF. SolidWorks will automatically open with the part ready to go into SolidCAM for programming. First, let's create our CAM part. Go to SolidCAM, New, Milling. When the New Milling Part dialog opens, we will use the default settings and save our CAM part in the model file directory by clicking OK. Next, let's select our CNC controller in the Milling Part Data Manager on the left. Since the machining of this part will be performed on a 3-axis machine, we will choose the Haas SS3XG milling post as our CNC controller for this example. Next, we will define our coordinate system. Let's choose the Select Face option and we'll place coordinates origin to corner of model box. Let's click OK to accept. Now we click OK to accept the default Z levels. Next, we will define the stock material for this job. Since there is already a solid body created representing the stock material, we will define this stock by a 3D model. Similarly, let's define our target and click OK to accept the selection. Now we can click the green check mark to complete the CAM part definition. To add a new iMachining operation, right-click on the operations header in the SolidCAM Manager tree. When the first iMachining operation is added to our CAM part, we will need to define the machine and work material parameters for the iMachining database. Note these buttons at the bottom left of the dialog. They enable us to manage machine definitions in the list. The new icon enables us to add a new machine definition. The delete icon allows us to delete existing machine definitions from the list. The Save As icon enables us to save defined machine definitions under specific names and locations. Finally, the Revert icon enables us to return all the edited parameters to their default values. For this exercise, let's create a new machine database. Under the machine list, click the New icon. A dialog will prompt us to enter a name for the new machine database. Let's name it Haas SS New. Clicking Save adds the new machine definition into the list. In the General section, define the major machine parameters. The parameters marked with yellow highlight are mandatory. Set the spindle speed max to 12,000 RPM and the feed rate max to 21,160 millimeters per minute. For reposition feed rate, set the value for XY movements to 10,000 millimeters per minute and the value for Z movements to 3,800 millimeters per minute. Set the spindle power max to 20 kilowatts. Click Next to define the work material. Choose the aluminum option with a 100 Brinell hardness number and a hardness Rockwell of 60 on the B scale. Click on the Finish button to confirm the machine and work material parameters definition. If you are running a demo version of SolidCAM, Select the default HAS-SS database and choose the same aluminum 100 BHN 60 HRB for material definition. Now that we have created a machine database for iMachining, we can select it in the CAM part definition dialog box upon creating any new CAM parts. Once we have confirmed the machine and work material definition, click Finish to display the iMachining operation dialog box. We will use the default iRough technology to machine the outside contour of our part. Let's click on the Define button to define the machining geometry for the current operation. When defining geometry in iMachining, it is important to note that the geometry is defined as a pocket that can be open, closed, and/or semi-closed. The pocket can contain internal chains treated as islands or used for safe tool entry. We will discuss many examples of defining geometries in Chapter 7 of this interactive Jumpstart PDF, concluding with iMachining Professor. For this example, the geometry is defined as an open pocket with island. Select the two chains as shown. Mark the outer chain, chain 1, as open to enable the tool to approach from the outside. In the Level section of the Geometry Edit dialog box, click on the Depth button to define the lower machining level for the operation. Pick the depth on the bottom edge of the model as shown here. We can also define these upper and lower machining levels on the Levels branch of the iMachining Operation dialog box. Moving down the tree, next we need to create a new tool. Clicking Select will bring up the tool table. Click on the Add Milling Tool icon. We'll add an end mill with a 9.5 mm diameter. Then we'll define the tool parameters. Set the total length to 76 mm, the outside holder length and shoulder length to 29 mm, the cutting length to 25 mm, and the number of flutes to 4. Now, let's switch to the iData tab and choose the 45 medium value for the helical angle parameter. This parameter affects the cutting conditions and step-down values generated by the wizard. Click Select to confirm the tool definition. Next, we'll define the milling levels. In addition to the depth specified at the stage of the geometry definition, we can define the delta depth to perform machining deeper than the part bottom edge. Let's set the value to -0.76 mm. Let's switch to the Technology Wizard branch. This wizard automatically calculates the cutting conditions for the iMachining technology, taking into account the tool data and milling levels defined for the operation. We will go over how to use the iMachining wizard in greater detail in Chapter 7 of this interactive Jumpstart PDF, concluding with iMachining Professor. For this operation, let's use the default position of the machining level slider, 3. Finally, let's click Save and Calculate, then click Simulate. First, we'll run the simulation in HostCAD, and then the Solid Verify mode. The corners are cleared first during simulation, and then the entire contour is machined. Next, we will define the finish machining of the outside contour. Click on the Save and Copy button at the bottom of the iMachining Operation dialog box to create a copy of the newly added iMachining operation. The copied operation will perform finishing of the outside contour. When the copied operation dialog box is displayed, choose iFinish for Technology. Now, let's switch to the Technology branch. In the iRest Data tab, note that the previous iRough outside operation appears in the Parent Operation combo box, which means that the technological parameters of the current operation are inherited from the previous parent operation. Save and calculate, then simulate the operation in the Solid Verify mode. The finishing is performed in a single cutting pass. Next, we will define the rough and finish machining of the center pocket. Let's add a new iMachining operation. We'll use iRough for technology and define the geometry on the lower contour of the pocket as shown here. Pick the bottom face of the pocket for the machining depth. We will select the same end mill tool defined in the previous operation, and we'll also use the default Technology Wizard settings. In the link branch, let's use the default value of 2.5 for the ramping angle. This means that the helical ramping into the pocket will be performed at the angle of 2.5 degrees. Save and calculate the operation. Let's simulate it in the Solid Verify mode. We see that the tool performs the helical entry and then the pocket roughing toolpath. Save and copy the newly added iMachining operation to perform the finishing of the center pocket. Choose iFinish for technology from the dropdown. Under the iRough Data tab in the Technology branch, the previous iRough center pocket operation appears as the parent operation. Save and calculate the operation, then let's simulate it in the Solid Verify mode. The rest material is cleared from the pocket corners before the final finishing pass is performed. Lastly, let's define the rough and finish machining of the pocket ledge. We will add a new iMachining operation and again use the default iRough for technology. Let's define the geometry as a closed chain on the lower contour of the ledge, and then mark the selected edge being open, as shown here. Pick the bottom face of the ledge for the machining depth definition. We will use the same end mill tool defined in the previous operations, and we'll also use the default Technology Wizard settings just as before. Save and calculate the operation, then simulate it using Solid Verify. The tool approaches from the outside and performs the roughing toolpath, first removing the material from the middle of the ledge and then clearing its corners. Next, save and copy the operation to perform the finishing of the pocket ledge. We'll choose iFinish for technology. Save and calculate the operation, then click Simulate. Again, we'll run the simulation using Solid Verify. We can see that the finishing of the pocket ledge is performed in a single pass. Congratulations! You have successfully completed Exercise 1 of the iMachining Professor Jumpstart series, iMachining Walkthrough. We hope you found this step-by-step guide on the definition process of SolidCAM's iMachining technology to be very helpful. Please join us for Exercise 2 of the iMachining Professor Jumpstart series, iMachining of a bracket.